Hello everyone, this is Dr. Hopkins with the next video in our series for 106. And today we're going to look at the acid-base behavior of salts. So in particular, we're looking at the conjugate base. So, we talk about an acid and its conjugate base pair. We're using this term base. Does it ever act like a base? So let's investigate if we have a conjugate base of a strong acid. So let's set up the base dissociation with, say, Cl-, which is the conjugate base of HCl, one of our strong acids. So if we did this, Cl- would be a base, H2O is the acid, HCl would be our conjugate acid of Cl-, and OH- is our conjugate base. But you'll notice HCl is a strong acid. So anytime we put strong acids in water, they completely dissociate. So that means that basically there is no way, under no circumstances, can we ever make a strong acid or a strong base in water. If we put a strong acid or strong base, they will dissociate completely. So what we get is really no change whatsoever. Cl- plus water just gives you Cl- plus water. So the chloride ion does nothing. So what we call a spectator ion. So what about if we have a weak acid? So let's look at acetate, which is the conjugate base of acetic acid, which is a weak acid. So let's write out the base dissociation, where we have our acetate plus water gives us acetic acid and OH-. Now in this case, we have a product that's an acid, but it's not a strong acid. It's a weak acid. And weak acids exist mostly as the acid form in water, as well as the dissociated forms. So this equilibrium is allowed. It may not be preferable, but it's allowed. So how would we determine the Kb of this reaction? So let's use water. Again, we had talked about this in the last video. So let's add the acid and base dissociation reactions, and this is just for the heck of it at this point, for a conjugate acid-base pair. So we'll take our acid dissociation of acetic acid, which is shown here. We have acetic acid plus water, gives us H3O plus and acetate, and that's Ka. And then if we write the Kb with acetate and water, gives us acetic acid and OH-. Notice they're not exactly opposite of each other, but they're very similar. And if we were to add those together, and get rid of those that end up on both sides of the equation, so let's sum it up, the acetate and the acetic acid will cancel, and we're left with two H2Os giving us H3O plus and OH-. In other words, Kw. So anytime you add equilibria together, so if you sum these reactions together to give a third reaction, you're going to multiply the equilibrium constants of those two reactions. It actually comes from the fact that delta G is minus RT natural log of K, and if we're adding natural logs, it's the same thing as multiplying and so forth. But anyway, either way, we get Kw is Ka times Kb. We know Kw. We can look up Ka in the back of the book for the acetic acid. So our Kb is just Kw over Ka. And in this case, it's 5.56 times 10 to the minus 10th. So let's use that information and let's do a problem where we solve for the pH of sodium acetate. So we were talking about salts. So 0.1 molar, and we have acetate plus sodium. Problem is, what do we do with the sodium? We haven't dealt with that. We were just dealing with acetate anion. So if you dissolve this salt in water, so if we put sodium acetate in water, it's going to completely dissociate into the acetate anion and the sodium plus ion. So we know that the acetate's a base, but what we don't know is, what about the sodium plus? Is it going to act like an acid, or is it going to act like a base? It's actually not going to act like a base. So the question is it going to act like an acid? Well, the first thing we want to do is look at what would the conjugate base be. So if sodium plus were an acid, the conjugate base is sodium hydroxide. Sodium hydroxide is one of our strong bases. Just like the strong acids, you can never, under any circumstances, make a strong base in water. So our sodium also does nothing. It's just a spectator. It's like the chloride ion we had in HCl. So here we have set up the equilibrium, sorry, it's a little bit crunched on the side. So we have our acetate plus H2O. So we're going to do a KB problem. We're going to figure out the pH of our 0.1 molar sodium acetate. I haven't written the sodium. It's a spectator ion. We can ignore it. So we're going to ignore our sodium. We won't even write it. We'll just write out this one. Now we have an ice table. Remember, our initial concentration of acetate was 0.1 molar. Water doesn't factor into our equilibrium. And our initial concentration of the acetic acid, NOH minus, is 0. It's all 1 to 1, so when we do our algebra, that's minus x plus x, and plus x, we're left with x, and this is 0.1 minus x. Okay, so we have our equilibrium concentrations. We plug those in, and then this here. But I'm going to go ahead and look at, and you'll notice this is times 10 to the minus 10. That is 0.1. So we're going to assume, and safely I would say, that 0.1 is much greater, 0.1 is much greater than x. And so we will then plug in. So in the end, 5.56 times 10 to the minus 10th is equal to x squared over 0.1. It's a much simpler quadratic to solve. And so if we solve that, we end up with x. We solve for x, and then I have the pOH out of that is 5.13. So x is the square root of 0.1 times 5.56. So my pOH is 5.13 because x is our OH minus. So remember, this is a base. And so then we would just do pH equal to 8.87. And then the question is it a base? And it is basic. It's greater than 7. So if we put this acetate, the conjugate base of a weak acid, in water, we will get a basic pH because it acts like a base. And lastly, we're left with our takeaways from this video. So basically what we found is that the conjugate base of a strong acid is not a base. The conjugate acid of a strong base is not an acid. Those are both just spectators. Okay, that's actually one of the hallmarks of a strong acid, strong base, is that their conjugate base, conjugate acid do not work. The conjugate base of a weak acid is a base. We didn't show it, but we could actually do the same thing. The conjugate acid of a weak base is actually going to be an acid. That logically makes sense. And we're going to use this Kw to determine the equilibrium constants of the acid-base pair. So until next time.